the question.
I will stand up. Okay. Thank you.
I thank you. Et pour aller en arrière and to go further. Okay, this one and this one. Okay, okay.
Just test the page down.
Oh no, it's okay. Yes, yes, it's okay. It's okay. Yes, yes. Thank you. Thank you.
Sure.
Oh yes, thank you. Thank you so much. Thank you very much.
Gentlemen, good morning. It's my great pleasure to chair this session. I'm Zhao Guo from China. Okay. In this session, we will have 3 talks, and the first talk will be given by Professor
Dubois.
Yeah. Oh, please.
Oh, thank you, Zaoli. It's my pleasure to be here and to share the presentation with Paolo Filippi, who is in the room, and it's my great pleasure. As an introduction, I just recall you very classical things concerning D2Q9. And D2Q9, you have this matrix from the particles and the moments, and I have this scaling, which is a purely numerical stuff. And I have this all these moments. I will go back on the choice of moments afterwards. And in this slide, it is just the D2Q9, very well D2Q9 of Lallemand and Dumière, more than 20 years ago, more than 20 years ago, with a very old equilibrium, more than 30 years ago, which was proposed, which was evoked this morning in the Ilias lecture. And if you write this equilibrium in the terms of moments, you find these formulas. And what you see also that you have 3 families of moments. You have the conserved moments, the Eulerian moments, and you have the other moments that I call the viscous moments. And this was also present in the lecture of Ilias just previously. With the MRT, you have this relaxation stuff. And I have to manage with 4 coefficients, S relative to the energy, X relative to this other second order, QY, SQ relative to something related to the heat flux, and the super energy with SH. All these relations can be rewritten in this vocabulary with non-conserved moments, relaxed with this kind of relation, with this matrix composed by all the moments. Okay. With this, in this framework of D2Q9, I have 2 important things in my hands. I have the equilibrium of the non-conserved moments, and I have all the matrix of relaxations. And with this writing, I can write a lot of several lattice Boltzmann schemes, including vectorial Boltzmann schemes. And you have the relaxation and the advection, and the advection is a case where the Courant number is equal to 1. With all this classical stuff, you can recover up to some difficulties that I will not speak about these difficulties now. The Navier-Stokes equations, and for the Navier-Stokes equations, you see that it is necessary to have this sound velocity, which is the famous value of 1 over square root of 3, and you have this shear and bulk viscosities that appear, and the sigma coefficients are related to the relaxation coefficients with these relations that were first proposed by Michel Hénon. Therefore, all that is completely classical, and there very quickly I will speak about this ABCD decomposition of the advection operator. With MRT, I will introduce the MRT scheme with projection. I will write quickly on the PDEs, equivalent PDEs, and first numerical results. Okay, what is important is to look to this linear advection, and therefore to write this linear advection in terms of the moments. And in terms of the moments, you can rewrite this relation in terms of the exponential of this operator. This operator is just the advection operator conjugated by the matrix of Dumière, which is the advection operator is the basis of moments. And the simple shift is just an exponential operator. And this exponential operator can be expanded in terms of this advection operator. Therefore, the ABCD method is just the fact that you decompose this advection operator in the natural basis of the problem, which is associated to the conserved moments and to the non-conserved moments. Therefore, you have the coupling between the conserved moments, coupling between conserved and non-conserved, coupling between non-conserved and conserved, and coupling between non-conserved moments. And what is important is to remark that the lambda square there can be computed with the very, very elementary rule of the product of two matrices. For the D2Q9, you can compute this advection operator, A with this there, B in blue, C in red, and D in green. And you see that we have a lot of zeros there, and therefore we can split this second family of non-conserved moments into two categories: the viscous moments that are used to recover the viscous terms, and this fourth order moment, which has no influence on the second order equivalent PDs. And all this decomposition was also presented by Ilias this morning, but was, of course, studied in the first paper, in the reference paper of Lallemand and Luo, and also in the papers of Paul Dellard and Martin Geyer some years ago, and so to a lot of other people. But with this decomposition, we have made the link between what I developed with the Taylor expansion method with the Chapman and Skog multi-cascade analysis. And we have revisited this in a previous paper. And all the Chapman and Skog at second order can be written like this. At first order, you have the gamma 1, which is AW plus B plus B phi. Phi is the vector of equilibrium. And at second order, you must decompose the non-conserved moments at first order. Therefore, this psi1 has this non-so-trivial expression, and therefore you introduce this Hénon matrix, and therefore gamma 2 is just, as a very compact form, is B times sigma times psi1. And this is all for the second order analysis. But now I begin the part of this lecture today, and you see the lecture is to remark that you have a fanciful block of zeros, and also one there, and also one there. Therefore, this matrix can be decomposed in a 3x3 block matrix with this anti-diagonal set of 3x3 blocks of zeros. And after that, it is natural to decompose the equilibria into two families, just the family of Eulerian moments and the family of viscous and other moments. And therefore, the psi1 is decomposed into two vectors. And the remark, the important remark, is that with Paolo, we worked a while, some years ago in Curitiba, in order to make the link between the regularization of Lat and Chopard, the recursive linear regularization of Malaspinas, and also the higher orders of Matila and Paolo relative to how to understand this in the MRT framework. And all these guys are working with Hermite polynomials, and we don't need Hermite polynomials in the framework I'll propose. Therefore, the important remark is the following, that at equilibrium, you can rewrite these red relations in terms of the W relations in black, and this equilibrium for the energy. Therefore, this relation, which is just a relation, a kind of recurrence relation, it can be, in some generality, written by the equilibrium of the viscous moments is equal to some matrix K times the conserved moments plus another matrix L times the equilibria of the Eulerian moments. And therefore, this decomposition is some analogy with what is known relative to the Hermite moments, and you have these two matrices. Therefore, this relation in the K and L are not unique. Therefore, this decomposition is some recurrent relation, and now we can define the multiple relaxation, the multiple MRT coming from this relation. We have three steps in this new scheme. We have the first step, which is a projection. When you consider the moments, you project the moments, saying that the two first components, the conserved one and the Euler one, are not changed, but you change the viscous ones according to this relation. But at this step, you replace you replace the second moment by the non-conserved, by this non-conserved part. Therefore, you have this projection step. And after this projection step, the trick is when you consider the equilibrium of this guy, you replace this guy by the equilibrium, and you doesn't change the equilibrium due to this a priori relation. After that, you have the relaxation, and for the relaxation, you have YE, which has to be taken after the relaxation. And if you look to the YE after the relaxation, you have this new relation, and you have this new relation instead of this one for the classical MRT. Therefore, the only coefficients you need to define the relaxations are the one associated to the Eulerian moments. Therefore, you have less number of relaxation coefficients. And after that, you have the propagation, which is not changed. Okay. After that, we have a small theorem saying that with this new scheme, you recover the same results, the same theoretical results that in the previous stuff. The proof is detailed at the end of the slides. I will not have the time to present there. Therefore, because of the fact that when you look carefully to this scheme, it is very close. It is not completely, yes, you look this relation, the scheme due to this set, all this set of zeros, this scheme is very close to the version of the lattice-Boltzmann, of the MRT lattice-Boltzmann with the last coefficients equal to 1. Fine, okay. And when you do that, it is natural to compare this new scheme with the version of the MRT with the last coefficients equal to 1, which is they are taken at equilibrium, as was mentioned in the lecture of Ilya this morning. Therefore, this is a Mignon and Brown test case with these more or less classical values. With this coefficient, when I consider BGK, it's not diverging, but the solution, the classical solution, is not recovered. And for this stuff, when you compare MRT and MRT with projection, it's more or less difficult to see the difference. Therefore, you can see that it is a good say to say that the projection is close to this version of MRT. But now we switch to the lead-driven cavity, which is an original illustration from the GIA paper more than 40 years ago. And for the GIA cavity at Reynolds equal to 1,000, if you look to the streamlines, it is they are very close to the previous version of MRT with this new scheme. If you look to the vorticity, you can see the same remark, even if it is not exactly the same field. And we don't see it, but what is written, it is that you can go further to the value of 1.7 for SE. This is for 1.98, I think. So you can extend the field of SE, therefore you can reduce the bulk viscosity. This is a comparison of this new scheme with very classical results obtained by Botella and Perret. And this is a cavity with this value of extended with a lower bulk viscosity. Therefore, it is natural now to compare the scheme with as a first test case, in the case where you have acoustics, where the bulk viscosity is very important. Therefore, I consider a test case with an initial profile, Gaussian profile around 1, with a delta rho which is not so big, and a radius which is adapted to this problem over the same relatively crude mesh. And I look to this is the initial condition, and this is the initial condition relative, when in abscissa you have the radius up to the middle of the figure, and therefore you have the perturbation of the density. And this is MRT with this, this is MRT with very standard coefficients. It's a shame that there is this spurious, No, it's not possible to have a correct. So this is MRT with relatively standard coefficients. And you see, when you look now to the function after a certain time of the density of the ratio of the density as a function of the radius, it is not bad, but it could be better because the problem is invariant by rotation, and therefore you see some noise due to the fact that the scheme is not perfect. This is the MRT with the two last relaxation coefficients with a relatively important value of SE and equal to SX, and the SQ and SH are equal to 1, and you see a wonderful beginning of instability, and you see this instability there, and therefore the solution of this MRT with SH equal to SH version is not correct. Now, this is the scheme with a projection. With this projection, you have a quite perfect propagation of the wave. And you see, when you look to the density as a function of the radius for a fixed time, you see that you have a very, very much better propagation, which means that this projection scheme has a lot of good qualities which were not present in the previous version of MRT. But, cerise sur le gâteau, thank you. If you look very, very precisely of the best quality, of the best properties of MRT that can you extract with isotropy at fourth order, you look to our old paper 10 years ago, and you see that with very, very strange coefficients, well, they are not secret, but they are very, very strange. You have SE equal SH, SX equal to SH, which is 1.99, and the other one is completely foolish. The product of the sigmas is equal to 1/6. And you see that with this very, very nice lattice-Boltzmann scheme with this value of the coefficients, you recover a result which is completely correct point of view of the isotropy. Therefore, as a conclusion, we have tried to give a new version, if you wish, of the projection scheme with the MRT framework without any use of the Gaussians and the orthogonal polynomial. Just remark that you have this relation. Therefore, you have 3 steps. And what is important is all this analysis has been helped by the fact that you have this advection operator in the basis of moments. It is natural to compare the MRT with these last moments at equilibrium, but the new quality of this scheme, what we have discovered experimentally, is the fact that we have a low ball viscosity. I think it's all. Yes, no, it's not all. Thank you so much.
Yeah.
Your coefficient are very close to 2. So
yes.
You studied the stability.
In fact, these coefficients are experimentally taken very close to the limit of instability in order to have the highest, the lowest viscosity, if you wish. For the other values, the scheme is experimentally stable. But you have to make attention to the value of the velocity and so on.
Please. Thank you very much. Is the projection somehow formally equivalent to switching to a Hermite space?
To what?
To a Hermite moment space.
What is that?
You mean the Hermite polynomials?
I don't know. I don't wish to know what is an Hermite polynomial because I don't need it. So it is just an analogy. I think that with Paolo, we will discuss this point. But when we wanted to know what are the analogous, we didn't find this analogous scheme.
So maybe my question, how did you come up with the projection? Like, was it natural choice? Or...
No. I read carefully the first paper of Jonas, and I read carefully the notes I have got with discussing with Paolo. Therefore, I saw that all these recurrence relations in the Hermite polynomials have an analogous. So I don't say that it is the same thing, that I said it is completely inspired with the previous work, of course. Because we were looking we were searching to have this kind of property at the beginning. Therefore, I cannot answer directly to your question, but the inspiration is completely clear. You're welcome.
Okay. Is that okay? No. Yeah, Professor, I have one question.
Yeah.
We know that in the original MRT,
Yes.
the relaxation parameters
Yes.
also influence the accuracy of the boundary condition.
So the boundary condition?
Yeah, it's also
Oh,
influenced by
oh.
the relaxation parameters.
Yes.
In the prediction method, does the parameter also influence?
Good and difficult question. I don't know, because
Okay.
they are the first test cases. I have got test cases with this lead-driven cavity where I have to manage with quite relatively difficult boundary conditions, but I have no precise answer to your question.
Okay,
I'm sorry.
thank you. Thank
You're
you.
welcome.
Yeah, because of the time restriction. Thank you. Thank you.
Thank you. Thanks to you. Thanks to you.
Now come to the next. The next topic will begin by Dr. Simulus. Please.
Because we record, you have to put this.
Yeah.
You stand up. 5 minutes left.
Okay. Yes. Okay. So welcome all of you to my talk. First of all, thank the organizers and thanks to the chairman. Today I would like to talk about spectral effects of entropic multi-relaxation for lattice Boltzmann methods as it was introduced today by Ilya. And these are the results of a recent collaboration between our research groups. So I would like to follow a different route than Francois in terms of not doing the numerical analysis by pen and paper, but by scientific computing, right? So the motivation will be given first, and I have a few words about the methods I would like to use here, and then also the numerical experiments that are a centerpiece of this talk. And afterwards, we will get a brief conclusion and an outlook to what to actually do with these kind of schemes. So motivation is, as you all might know, lattice Boltzmann methods are extremely good for computing 3D non-stationary fluid flow results, right? So everything is time dependent, fully three-dimensional and so on. However, standard lattice Boltzmann methods, for example, the BGK single relaxation time model, they're usually only stable for some kind of grid Reynolds number in the regime of 10 roundabout, right? So once you want to go below this grid resolution and still have high Reynolds number solutions, you can use some stabilization techniques, for example, large eddy simulation borrowed from macroscopic methods, or for example, you can do entropic collision, right? As was proposed in 2014-15, I guess, by Carlin and others. So my question now is, this is all fine, but what are the numerical effects of these KBC relaxation times, right? So what is the experimental order of convergence in numerical test cases for 3 dimensions, and so on. So my approach here is, as I said, different. So I want to computationally analyze the KBC model by just using a very efficient parallel open source software, which is called OpenLB. So speaking about the methods, what I want to do here is to approximate Navier-Stokes equations in an initial value problem setting. So no boundaries, no force whatsoever. However, we have a initial condition, which is usually assumed to be in L2 diff, so it should be square integral and somehow divergence free. And as I said, the dimension is 3 here, so we don't want to go below this because we want to have the real results for the applications in the end. So the usual thing, we want to approximate this velocity vector u here, and as soon as you put the viscosity epsilon to 0, the Reynolds number will increase to infinity. And usually in that incompressible Euler limit, you will get some instabilities of the method. So fair enough. we can have an approximation of this PDE by discretizing the Bhatnagar-Gross-Crook BGK Boltzmann equation. And as it can be formally proven, this is limit consistent towards the Navier-Stokes equation with an order of first order in time and second order in space, because we use diffusive scaling here. So this is a very simplistic written down version of the Lattice-Boltzmann equation you all might know. However, I have just skipped the space dependency because, as I said, we use diffusive scaling, and the viscosity is then reproduced in the limit, and also the incompressibility, since the Mach number is going to go to 0. So in this case, we have BGK collision, where this matrix K here is then just reduced to a scalar 1 over tau, where tau is the relaxation time, and then you can recover the velocity as a first moment. So far, so good. That is what you all might know. Then what you also might know is that we want to choose some kind of computationally efficient velocity set here. So it's a D3Q19, and then also some kind of basic discrete Maxwellian. So it's a second order approximation, second order polynomial equilibrium, basically. And then we want to use a collision matrix here. So we want to have natural moments, m to the power of -1 times a matrix S times m. And here is the difference. So S is now space-time dependent, since it is a relaxation function, basically, motivated by these KBC relaxations. So how does it look like, the relaxation function? On the right-hand side, you can see a table, right, which summarizes all of the moments by their order, right? And the kinematic ones are the conserved ones, so they are relaxed trivially to equilibrium, setting this relaxation frequency to 0. Then we have the shear moments that are second order and basically connected to the viscosity, right? So this is the 1 over tau value, basically. And then you have the kinetic ones, which are the higher order moments that are relaxed with a relaxation function gamma star here. And as proposed by Carlin and others, this is given here. So it's a relaxation function which takes into account some kind of deviation in terms of non-equilibrium parts, which are then written in an entropic scalar product, which is relative to these higher order moment relaxation times. So the claims now are, first of all, that we approximate the Navier-Stokes equation for fixed epsilon, right? So we fix the Reynolds number, put it a little bit higher than usual, and then we approximate the Navier-Stokes equation in 3 dimensions. Claim number 2 is that we have inviscid stability. That means I can always find some kind of configuration where this grid Reynolds number is substantially higher than for the BGK single relaxation time model, where this particularly breaks down, but the KBC still is stable. Claim number 3 is that we have a BGK limit consistency. That means there is this famous proof of Saint-Germain that we have BGK Boltzmann equations that then rigorously converge to some kind of Navier-Stokes equation. Since this is the case, and we know this, we want that in the limit. So for higher resolutions, lower spatial grid parameters, we then have a limit towards the BGK relaxation time, right? So these are the claims, and the goal is now to numerically approve these 3 claims by doing 3-dimensional simulations. So let's look into these. The video doesn't show because I cannot use my own laptop, so bad for you. However, I would like to approximate the incompressible Navier-Stokes equations, and I do this by initializing a Taylor-Green vortex data, which is given here. And yes, so I can compute these usual quantities as is given also in the literature. Always it is a dissipation rate, a total dissipation rate dependent on time. And here we also do the arrows because we're interested in this. Then there is an energy spectrum, which is also classical. And then we propose a new quantity, which is called relaxation spectrum, to analyze this in Fourier space. And then we also can compute something which is called maximum vorticity to see how all these quantities somehow interact. Okay, so let's look at the first claim. The claim was that we approximate the Navier-Stokes equation. So we pick a very basic set of parameters, which is a Reynolds number of 3000. Then we have a resolution which is fairly low, which was the aim. And then we have like Mach numbers, which are used in practice for kind of weakly incompressible simulations. And then we measure the error here. So the first one is just a deviation from the reference data, which is a pseudo-spectral DNS, so very high result, fairly accurate, and which can be done over time. And then we have a total total error, which is averaged over the temporal nodes or temporal discretization steps we use for comparison. So what is plotted on the right-hand side here is on the top, there is an error plot over time. So this is time in seconds proceeding for the simulation. And then this is the time-dependent error of each resolution for the KBC N1 scheme. So as you can see, on average, it somehow decreases further down, up to like, down to like 1%. And as soon as you compute the experimental order of convergence, so the slope of the decrease of the error, then you can see that on average over time, this goes around 2. So it's a second order method with respect to space discretization towards Navier-Stokes pseudospectral DNS results. Claim 1 is finished. So claim 2 was this is invisibly stable. So for seeing that, we can then increase the Reynolds number a bit until 6,000 and plot like the usual energy spectrum results, which are given here in black. So black dashed is the single relaxation time BGK, which becomes apparently unstable after some time. And these are the time steps where the SRT BGK becomes unstable, right? So this is what you see here. And then as expected, or as we wanted to see, is that the KBC scheme still is stable and reproduces this kind of famous -5/3 law of Kolmogorov as soon as you approximate larger Reynolds numbers. Now, the interesting part is that we can define a new quantity, which is called a relaxation spectrum here and denoted by C. And this is actually the same as the energy spectrum, but we now replace the energy density with the relaxation time or frequency, right? So this relaxation function density is then first Fourier transformed, then plugged into the band average, then computed similarly as the energy spectrum. So as it turns out, this actually counteracts the -5/3 law by being just +5/3 scaling in the power, right? So you can see that the blue line is this relaxation spectrum, and it just is physically fine. So stable results, physically fine. And since the solver is so efficient, we can just plot the energy spectrum for all time steps, right? So in each time step, we just Fourier transform everything, transform it back, and then plot the spectrum. So visibly here is also that as soon as the control spectrum goes up, the energy spectrum goes down, right? So you have increased dissipation at the smallest scales, so near the highest wave number cutoff. So the finding number 2 is that this KBC relaxation is actually stable for all tested configurations, and we have a relaxation spectrum that has a +5/3 law, which is physically nice. All right, the last claim I want to present today is that we have BGK limit consistency. So to have a look at this, we can then measure the spatial mean of this relaxation function, which is just the spatial mean over all the grid nodes, and then also compute a kind of variance of this, right? And if you plot all of these, again, for a high Reynolds number, diffusive scaling for the Mach number, and then several resolutions, you can see that all of these kind of spatial means and variances, they kind of tend towards this number 2, that is the BGK limit, right? So as soon as we refine the grid in diffusive scaling, all of these relaxation functions will vanish towards a BGK collision. Once again, you can then also measure this kind of slope, right? So you want to not only know that it does this, but how it does it, with which speed it does it, and the convergence order is once again over 1, so roughly about 1.5. So the interesting part also here is that once you look at these kind of spatial means and variances, you can then just plot the vorticity and see that it's actually just flipped. So once again, as before, we see that the method, the relaxation, KBC relaxation just tracks the small scales and pushes in some dissipation to actually achieve a stable result. So with that, I want to come to the conclusions and also the outlook of the work. So the conclusions are brief and concise. The method insights here are generated from the efficient LBM code OpenLB, so we can actually use these algorithms to generate knowledge about the method itself. Then there was a new notion of relaxation spectrum we proposed based on these results. We then have numerical observations summarized here. So the KBC LBM is approximating Navier-Stokes with second order. It is invisibly stable for all the configurations we tested, and it also is limit consistent towards a BGK single relaxation time, even for this very efficient configuration of non-entropic equilibrium and reduced velocity space. So the outlook of this is, since we have reproduced fairly high Reynolds numbers with very low resolutions, we can then do Monte Carlo KBC LBMs for fluid flows with uncertainties. So here, usually you increase the Reynolds number, right? And then you want to see some kind of convergence. And the samples are usually also increasing with the Reynolds number. So this first plot is generated with 32 samples, then it's 64 samples, then it's 128 samples, right? So 128 times the same computation. And as soon as you average the mean, you can see that this actually converges to something which was just recently proven. So with that, I would like to cordially invite you to our spring school, which is happening next year in May. It's in Marseille at CERM. There are very many famous speakers we invited here. If you want to know more about this, just scan the QR code. And with that, I would like to thank you for your attention. Please ask questions.
Thank you. Yeah, I have just a question.
Yes, please.
About the relaxation of the C, the parameter C is just the relaxation. You mean just the relaxation parameters? C.
The C was the newly introduced.
Yeah.
Yes, yes. So
Yeah.
somehow I cannot.
It's observed that it increase with the wave number. Increase with the wave
Yes,
number.
yes,
Yeah.
increasing.
So basically, with the increase of with the increase of the wave number, this means that at the small odd city.
Yeah.
So this means that the local news number is large for large wave number. So actually, in this parameter reflects the non-equilibrium effect. I think so. Yeah, because in the parameter, you just include the correction term in terms of the non-equilibrium effect.
Yeah, that's very
Right?
interesting. Yes, yes.
Yeah, it is very interesting.
Yeah, so
Yeah.
we could, for example, also plot the local Knudsen number to see the correlation. Yes,
Yeah.
very interesting.
Yeah, I think the local Knudsen number is also related to this parameter.
Okay,
Yeah.
very nice.
Okay,
Thank you for.
Thank you. Any questions or comments? No, thank you again.
Thanks so much.
Okay, the last talk will be given by Dr. Ananda, please. Yeah.
You also have a pointer if you like.
Yeah, sure.
From behind. There it is, right. Just you can put it like that. Okay. So can I help you?
Yeah, thank you. I'll be talking on a study of lattice-Boltzmann methods based on vector kinetic models. Several works have been done in the literature on the analysis of lattice-Boltzmann methods. I would like to mention a few of them. So first is the Chapman-Enskog expansion, which involves multiple scale expansions of particle distribution functions in order to obtain a modified PDE for the system that we will be solving. So some of the fundamental works in this direction are mentioned here. And next is the equivalent equation method of Francois Dubas, which involves Taylor expansions in order to obtain a modified partial differential equation. And then we have the multi-step finite difference form, where the lattice-Boltzmann methods are shown to be equivalent to a multi-step finite difference equation for the limit equation that we'll be solving. So several works in this direction are mentioned here. And these methods, they are for the standard lattice-Boltzmann methods, which are derived from the Boltzmann equation, which involves a scalar particle distribution function. On the other hand, we'll be considering another set of models called the vector kinetic models or the discrete velocity Boltzmann models of Arikbad, Riole, and Natalini or Francois Bouchou. And these models have vector functions, and in the limit they'll be they'll solve the original equation that we want to solve. So some of the works in this direction are the implicit kinetic relaxation schemes by Khule et al. And from Raghurama Rao et al., there are methods like lattice Boltzmann relaxation schemes, which can solve compressible flows as well. So I'll be focusing on lattice Boltzmann, some models, vector kinetic models, and try to do analysis for those in this work. So this is the hyperbolic system of conservation laws, where U lies in Rp and Gd of U are flux vectors in the direction d. So capital D is the total number of dimensions, and P indicates the number of equations. And this is the vector kinetic equation, where F also lies in Rp, same as that of U. And F equilibrium as well lies in Rp. So Q will be the total number of discrete velocities. So as epsilon goes to 0, from this equation, we can see that F goes to F equilibrium. And hence, we have a perturbation of F equilibrium. So F is a perturbation of F equilibrium. And if this moment relation is satisfied, then if we sum this equation over all discrete velocities, then we have this expression. So and also as epsilon goes to 0, this will solve the original hyperbolic system if the equilibrium, if this moment is satisfied by the equilibrium. So, so vector kinetic equations approximate the hyperbolic system of conservation law, and we'll construct a lattice Boltzmann method for this vector kinetic equation. So the transport part of this equation will be solved along the characteristic, and this will be solved using the collision algorithm. So basically, in the usual lattice Boltzmann method, this is treated at time step t, and both the terms F and F equilibrium, they are treated at time step t, and this will be solved using the characteristics. So if we do that, we get the standard lattice Boltzmann equation with omega equals delta t over epsilon. And and we also consider another lattice Boltzmann equation where we treat F implicitly and F equilibrium explicitly, and therefore we get this expression. And upon simplifying, we get something like this, where omega tilde depends on omega. So if we notice the two discretizations, the explicit and the semi-implicit one, they are basically similar with different values with omega and omega tilde. So in this work, like to have a general analysis for both of them, we use this parameter omega hat, which will represent omega in case of explicit and omega tilde in case of the implicit one. So this is the standard lattice Boltzmann algorithm with collision and streaming steps. And the equilibrium functions in the lattice Boltzmann equation, we saw that they need to satisfy these moment relations already in order for them to approximate the hyperbolic system. So in the classical D1 Q2 way, for two particles moving towards left and right, we can have the equilibrium functions in this form. And for D1 Q3 way, we can have like for where two particles are moving to the left and right, and one is steady at the center. For that, we can have this kind of equilibrium function. And next, we can also introduce upwind functions, where the equilibrium, where the flux vector can be split into positive and negative fluxes, such that G will be equal to G plus minus G minus. In that way, for the positive moving, for the right moving particles, we can have positive part of the flux, and we put the negative part of the flux for the left moving particles. And this for the particles at rest, we use this in order to satisfy these moment relations. So this will result in an upwind discretization eventually. So next, upon doing Chapman and Skoog expansion of this model of this lattice Boltzmann equation, we'll have a numerical diffusion term, And we can, for the numerical diffusion coefficient to be positive, we have this condition on omega hat. So it should be less than 2. And for explicit LBE, where omega is delta t over epsilon, we put an upper bound on delta t. Whereas for the semi-implicit LBE, there is no upper bound on delta t, so we only require delta t to be positive. And but we already have a relation between omega and omega tilde, which is this. So which implies that omega tilde is always less than 1. So omega tilde is anyways restricted to the interval 0 to 1. So which is depicted in this region. And next, I'll be trying to show H inequality first for the semi-implicit discretization. For the semi-implicit discretization of the lattice-Boltzmann method, in order to do the H inequality, I'm using these following notations for convenience. So at t plus delta t, I'll be using xi n plus 1. And for this term, I'll be using at n, time step n, and yi. And similar for equilibrium. So if we consider a H function, which is convex, and which satisfies this minimization property, then for this lattice-Boltzmann equation, which is the semi-implicit discretization, there will exist an entropy, a H inequality of this form with omega to be positive. Now, this H inequality can be rewritten as like this. And upon simplifying, we have something like omega tilde in this expression. So due to minimization, like when we take moment, like when we sum them over all q, due to minimization, we'll have this H inequality, like which satisfies like H at time step n plus 1 is always lesser than equal to H at time step n. So this is so we have seen that for the semi-implicit lattice-Boltzmann equation is always satisfies the H inequality. So now let us see the general discretization of the LBE, which includes both explicit and semi-implicit. So in that case, taking H over all whole of F, and this is a convex combination. For this to be satisfied, we require omega hat to be less than or equal to 1. Then then the H inequality will be satisfied. So for the explicit case, we always need to enforce this condition in order to have H inequality, whereas the semi-implicit one is always satisfies the H inequality. Next is the finite difference form. Here I'm trying to show that show the finite difference equivalent of the lattice-Boltzmann method. So the lattice-Boltzmann method, the lattice-Boltzmann equation is of a form. We can show that it will be also equivalent to a finite difference method corresponding to the hyperbolic system of conservation law. For this, I'm using these notations for simplicity at time step t plus delta t, again n plus 1. And for this at I minus mq and time step n, similar for equilibrium. And this lattice-Boltzmann equation, this is the lattice-Boltzmann equation that we have. This is the general LBE, either explicit or semi-implicit. It holds for both. So with omega hat. So this is the general lattice-Boltzmann equation, and it is equivalent to this recursive equation with which consists of linear combination of equilibrium functions at various time levels, at all previous time levels actually, if we consider f to be equal to f equilibrium at the initial time. So if we consider that, then the lattice-Boltzmann equation is equivalent to a recursive equation, which involves equilibrium functions at at all previous time levels. Then in this, this is the equivalence. This is still still at F level. In order to move it to the level of the hyperbolic system, I'm substituting the expressions for equilibrium function. So I'm considering the upwind equilibrium functions, where F1 is the positive flux and F3 is the negative flux, and this is the rest. F2 is the rest particle function. So summing it up, we have something like this. So which is basically this one. So now I'm using this calligraphic U to denote this sum, which is basically sum of these quantities over here. So which we can say that it is nothing but an upwind discretization with a modified delta x. So now, like summing up the whole this equation over all the discrete velocities, we have something like this one. This is the this is a finite difference equivalent of the hyperbolic system of conservation law. So basically, using the lattice-Boltzmann method, we are solving this expression for the hyperbolic system of conservation law. And if we have omega hat to be less than 1, then all these terms are positive, and the numerical diffusion coefficients corresponding to these upwind differencing, they all sum up, and that's why we always experience like very high numerical diffusion for this range of omega hat. And next, I would like to talk a bit about consistency. Uh, and these calligraphic cues, which we saw over here, they can be like under under the assumption that all the variables involved are smooth, we can do Taylor series expansion and observe this. So now, using these inside this expression, we see that we have this big expression, and we can see that this is equal to 1. So this term basically goes off, and this term can now be seen as this expression, like this delta t can be absorbed into this summation and this summation as like starting from j equals 0 in both of them, because this relation is true. So because of that reason, we can do this, and then like using this in the previous expression, we basically have this one. So we can see that these two are almost same except for this summation delta t and k plus 1 delta t, and similar here. So basically, if if delta t is same for all the time steps, then we have consistency. Or if omega hat is 1, then we'll have consistency, because essentially the j equals 0 terms alone will be valid. So next, a bit about total variation boundedness. And so if the total variation is defined in this manner, so total variation of all the variables in the hyperbolic system of conservation law is given by this. And if the equilibrium functions are such that the finite difference form given by the calligraphic U is bounded, then we'll have this one. And if in particular omega hat is less than or equal to 1, then we'll say our multi-step finite difference equation itself is total variation bounded. A bit about positivity. So same thing follows. If omega hat is less than or equal to 1, then we'll definitely have positivity. And this is these are some numerical results for the inviscid Burgess case, where we can see that with increase in omega, the L2 error norm decreases. So next, I would like to talk about another method, like another model, which is like hyperbolic system of conservation law with source term. For the same model, I'm just adding a source term. And to this model, in order for to approximate this one, for the vector kinetic equation, we add R. So in the limit, same thing follows, and taking moment. So basically, we are adding this moment as well to the previous case in order to approximate the hyperbolic system of conservation laws. So as epsilon goes to 0, if we satisfy this moment relation, then we'll be solving the hyperbolic system of conservation law with source term. So for the lattice-Boltzmann equation is same, except for here, except for R, we treat it using Crank-Nicolson method. And the collision step is here, is this one. This time t plus delta t term is absorbed to the left-hand side, and the streaming is done in this manner. And after finding this, after doing the streaming, in order to find U, in order to find the macroscopic variables, we need to solve this using Newton-Raphson's method. The Chapman and Skoog expansion for this lattice-Boltzmann equation will be like this. In addition to the usual numerical diffusion, we also have something like numerical convection. This is desirable, whereas this is not desirable. And so we need to nullify this numerical convection. So for that, we add this moment relation in addition to the usual, in addition to the moment relation which we saw earlier for the vector kinetic equation to approximate the hyperbolic system. In addition to the required moment, we also consider this one in order to remove the numerical convection. So these two relations are also satisfied by similar models as those for F equilibrium. So for it's almost same as what we saw for F equilibrium, just with U replaced by S and G replaced by Jacobian G S. So with that, these R's will satisfy these moment relations. Now some numerical results. So with one-dimensional discontinuity, this is the problem of Levick and E. The top one is the McCormack's method, whereas the bottom one is the lattice-Boltzmann method. So mu is like varying stiffness. With increase in stiffness, we see that the lattice-Boltzmann method still captures the discontinuities in the right locations. And this is for the 2D model. So with increase in mu, we see that the discontinuities are still at right locations. And similarly for the three-dimensional discontinuity at some cross section. And next is this is a D2Q9 model where like in addition to equilibrium, in addition to functions moving along the coordinate directions, we also have some equilibrium functions moving along diagonal to coordinate directions, and upwinding is done such that there'll be some balance between these variables in order to capture the diagonal discontinuities exactly. So these are the upwind terms along the different directions. And we can see that the discontinuities along coordinate and diagonal to coordinate directions are getting captured exactly. And next, to summarize, so I first presented a semi-implicit discretization of the vector kinetic equation along with an explicit discretization and compared them both with their relaxation with respect to their relaxation factors. And from Chapman and Skoke expansion, we had this relation on omega hat. That is, it should be less than 2. And for H inequality, total variation boundedness and positivity, we require this relation, which is a stronger constraint. But the semi-implicit one naturally satisfies this, and it always satisfies H inequality. And we considered a macroscopic finite difference form of the lattice-Boltzmann method, and using this, we also saw consistency with respect to the hyperbolic system, and then extended to source terms, and the numerical convection was nullified, and some progress in the direction of like the D2Q9 model where diagonal discontinuities are captured exactly. So if you're further interested, like please check out the article. Yeah, I'm done. Yes,
Okay.
thank you. Mhm. Yeah. Okay.
In the comments?
Okay.
The theoretical result is very interesting.
Okay, thank you.
Just one question. In the type 1 discretization,
Okay.
you mean just that the dirty over epsilon is just the relaxed parameter? Yeah.
Okay. The explicit one?
Yeah.
Okay.
Yeah. Does this mean that the time step must be very small?
Yeah, actually it should be less. Time step must be like, but omega can be controlled because epsilon is still free.
Okay.
So like omega and epsilon can be adjusted to fix a particular time step.
Okay.
But still we need to make sure that time step is same for all the times.
Another question is about the
Okay.
macroscopic
Mhm.
finite difference formulation in
Okay.
the derivation. You just assume that
Okay.
the initial condition is at equilibrium.
Yes.
Yeah.
Yes.
Does this apply to unsteady flow? We know
Okay,
that
when
for
the-
unsteady
okay,
flow,
okay.
the initial condition should include
Okay.
the non-equilibrium effect.
Okay,
In
yes,
this case,
in that case, we should modify the theorem such that like even the expression which only contained equilibrium functions, it should also contain the non-equilibrium quantities at the initial time. So it should probably be explored more.
Okay,
Yes.
thank you.
Okay, thank you.
Okay.
Okay.
No. Even though we now close this section and thanks all the speakers again.
Thank you.
Okay. I will now close this.